All right, testing 1, 2, 3, testing 1, 2, 3. I see green bars moving, that's good. I see the green circle showing up there on the monitor, that's also good. I see people in chat, also good. There's a dog crunching on a snacky snack down here to try to keep him calm, so if you hear little crinkle crackles in the background, that's Sirius saying hello. So, yeah, greetings, travelers. My name is Mike. Welcome to Earthshine Education, our live planetarium show. Yes, I know it still says stream starting soon. Just kind of clicking around on some things. Was hoping to have these all up before I started, but hey. We're live, so we're just gonna do it. We're gonna do it on the fly. Where's my moon phases? There we go. Okay, so what else do we need? We need Universe Sandbox, right? So let's get that running in the background. Get Stellarium rolling in the foreground. Let's get rid of this placeholder. Oh, you guys see what I'm looking at? Huzzah. Okay. How y'all doing? How was your weekend? Someone is calling me. That's not acceptable right now. Yes, that is what you think it was as a ringtone. Don't at me. I don't care. Okay, Sandbox Universe is up and running. Stellarium is up and running. And our web browser is also up and running. We are ready to go. Are you ready to go? What's everybody got for snack and for drink? I've got some green tea and some water over here. Hopefully you are prepared to hydrate yourself. Delicious. Have a snacky snack with you. Cold brew with almond milk sounds tasty. Got water as well, also tasty. I should probably get rid of these ginger ale containers that are just sitting here, huh? Alright. So, we have a lot to talk about today. Usually go over some stuff from the weekend. If you did or did not hear, the Mars rover that landed not too long ago, that's Mars Perseverance. It birthed the wonderful little Ingenuity helicopter. It's really a drone, but they're calling it a helicopter. The thing weighs less than 4 pounds here on the Earth, so it's really, really light. And there's the selfie that was taken from the rover, from the arm camera looking at the rover. And this helicopter, well, they did a test to see how the rotors were on the helicopter, and there was some sort of weird error between the quote-unquote pre-flight and then like the test flight while it was still sitting on the ground, and so they have delayed it. This was actually supposed to happen last night, sometime after like 10 or 11 o'clock my time. They were going to actually launch this thing up into the sky, but with the error, they have delayed it till the 14th, so today's the 12th, so actually in 2 days, so on Wednesday, we'll probably go live at a different time. We'll do our day show. If they do it at night, we'll go live at night and we'll cover this thing as it's happening. I don't really like staying up super late anymore. I really physically can't, but for this I will, because this will be the first, not necessarily this will be the first flight of a man-made creation on a different planet, and I want to be alive and awake to see it. So if I will force myself to stay up to see that. Hopefully you will come and watch it with me. We'll just restream the NASA one and do Mystery Science Theater style commentating over it and making jokes, because that's what we do here. We make jokes. We also talk about astronomy. That is the whole point of this. Let's get rid of... Oh, it's such a cute rover. Killing me. All right, we'll get rid of that. Then we're going to jump over to astronomy picture of the day. And if you don't know what this is, I always talk about it at the beginning of our show. Astronomy picture of the day, just look it up on any browser that you like, DuckDuckGo, Google, whatever. It gives you a picture every single day. Gives you a description on the bottom and, you know, image credits of whoever took it. This one actually was from the weekend, and it's a picture of Orion. If you don't know what you're looking at, you can usually click on it and zoom in, and sometimes it'll actually bring up little lines and show you what you're looking at. But Constellation Orion is right in here. You got Betelgeuse, the shoulder star. This is Bellatrix right there. This is Rigel, and then you have Scythe. So you got 4 bright stars on the outside, then you got Omnitak, Omninam, and Mintaka, the belt stars, and then you can actually clearly see the Orion Nebula. If you don't, we can actually see how well this is. Let's zoom in. Yeah, you can see the Orion Nebula just sitting there. So if you're out in the middle of nowhere, you get a beautiful sky, and you can actually see clouds in space. This is very, very cool. You got the Pleiades over here, and you got the face of Taurus the Bull. If you don't know what these is, if you're new to the channel, you're about to learn. You're gonna get learned. Get good, scrubs. We're gonna get good at astronomy. Let's see, what else we got from the weekend? Looks like Sunday was this, a video of black hole collisions. So this could be kind of cool. Yeah, that's freaky. It's like oil and water. Dun 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 dun. Ba-da-dun. Merge together. Yeah. So in astronomy, it's literally survival of the fittest. The biggest one usually wins. In this case, this is a simulation of black holes merging together. Again, you can't actually see a black hole, but you can see stuff around a black hole. The fact that this weird ring exists here, this is related to the what's called gravitational lensing. So imagine... How do I want to explain gravitational lensing? So imagine that between where you are sitting right now, or laying down, or wherever you happen to be, and you're looking at a screen, if it's a computer screen, or a laptop screen, or your phone, whatever it is, there's space between your eyes and the screen, correct? If you put a black hole between your face and what you're looking at, the light will actually bend around the black hole. Some of it will go into the black hole, to the backside of the black hole. Remember, these things are spherical in shape. But some of the light will actually bend around. That's actually this weird... It's called gravitational lensing. It's this weird line shape you see here. I'm glad I start off with a starting picture of the day, because again, this is always different every time. You can see it in lots of deep field photos. Let's see here. Can we get a gravitational lensing? There's the actual picture of a black hole, the event horizon around a black hole. This is actual real data, an actual quote-unquote photo of a black hole. The black hole itself would be in the middle. This is a donut-looking shape, and they, of course, were photoshopping that into horrible things because of the way it looks. I'm trying to find a picture of gravitational lensing. I just don't remember which image it is. There's a very beautiful image where you can actually see these weird streaks. Einstein actually predicted gravitational lensing when he wrote his thesis on general relativity, but it wasn't proven until much later. Here we go. So that effect that we saw in the video, that's what's going on with these little streaks. These are not black holes. These are actually galaxies, and the galaxies are so massive that they are bending the light of other galaxies that are behind them. So from our point of view, the light gets bent around the galaxy, or, you know, in the other case, it was a black hole. So this is an actual phenomenon. Again, it's called gravitational lensing. You see these weird streaks. It's not like the camera's out of focus or anything like that. This is an actual physical property. So this galaxy right here, this is massive, and way behind it, there is some sort of blue-colored spiral, and it's actually, you see a reflection of it here and here and here, and it's actually being stretched around. It's a very interesting phenomenon. I invite you to look it up on your own time. Again, that's called gravitational lensing. That only works if the theory of relativity actually works. Which apparently it does. Go figure. And that could change in the future as we learn more and more about science and astrophysics. It's always changing. So what we know now is vastly different from what they knew back in the 1970s. And what we know right now will be vastly different from what we'll know in 2050. So things will change. Today's photo on Astronomy Picture of the Day is the Flame Nebula and Alnitak. Now, Alnitak, you've already heard me say that name. This is one of the stars in the constellation Orion. It's one of the belt stars. This is actually what's called the Flame Nebula. It's not an actual flame front, but it does kind of look like a flame, right? That's that fractal. If you don't know what a fractal is, we're going to talk about that in the future. And they are incredible, and they are very intriguing. Fractals are patterns that you see. And the most famous of the fractal patterns that exists is what is called the Mandelbrot set. And this has nothing to do with what we're talking about in front of us, but I have to show it to you. So this is the Mandelbrot set. Everything that's inside the dark area that you see here, the math does not exist. Imagine divide by 0. But you see right along the edges, you see all these, like, you know, almost like lightning crackles. That's the same idea. That lightning crackles exist because of the way fractals work. Your lungs do this as well. Look at a tree and then look at your lungs, and they have the same style shape. You have a trunk in the middle, and then you have little branches and little more branches, little more branches. That's how your lungs are. That's how trees are. But here's the kicker. Remember the shape we started out with right up here? If you really pay attention, there it is again, but more complicated. And there it is again, and there it is again, there it is again. All these little dots you see there along the edges, you see one up here. It's the same shape, but more and more complicated. So as you zoom in more and more, you get incredibly detailed and incredibly crazy looking colors, and incredible looking math. So let's zoom in on a section. Let's do that. Boom. This is the exact same mathematical set, but zoomed in to a greater degree, and you still see it's replicating itself over and over and over and over again. You start to see what are called like seahorse shapes and things like that. You can change the color. There's actually a software out there called Chaos, X-A-O-S. If you're, again, this has nothing to do with what we were going to talk about, but this is what happens when we start talking about things. Where is it? There it is. Let's get you Chaos. So look it up, XAOS. It is on GitHub. You can actually generate your own fractals, and we will do this live one day, just as an aside. But fractal math, well, hopefully I'll be talking to Dr. Jonathan Wolf, who's the head of the Fractal Foundation in Albuquerque, New Mexico. A good friend that I haven't actually worked with in a very long time. But we will do a fractal thing and record it. We'll do like a little podcast between me and him, hopefully, and record it and, you know, get that out there to the masses. His website, by the way, is fractalfoundation.org. So if you're interested in learning more about fractals, it is fractalfoundation.org. So his website is down. Wonderful. I should probably call him and tell him that his website's down. Anyway. So yeah, that's what's going on. That's why we have that weird flame front looking thing. That's why you have these little branching arms. That's why if you use Photoshop or, you know, Paint Shop Pro or any of those photo manipulation softwares, when you try to generate clouds, it'll sometimes offer you Gaussian. You know, that's referring to a scientist named Gauss. But there's also fractal pattern, and it's a random generation. You see fractals every day. We see spiral galaxies, that's fractal pattern, because that's the same shape as what's called the golden ratio. The Mandelbrot set you see zoomed in, so to speak, as you look around in life. It's very interesting. Anyway, bright star off on the left, and you see this wonderful cloud glowing in the background. If you want to read more about it, just look in the comment section at the bottom of the picture. Strong picture of the day. You can do this on your own time, and you will see lots and lots of cool stuff. Always good to go through the archive. It goes back to 1995, and the pictures get smaller and smaller and smaller. But because technology was different back then. But it's always good. Look up your birthday or something. Just gonna look up a different birthday for the heck of it. This is not my birthday, but I'm just gonna look up February 5. Yeah, cool. Picture of the moon. With the Earth in the background from Apollo. Very cool. Description on the bottom. Again, pick a day. Doesn't matter whose birthday. Someone you know. Someone with us, or no longer with us. Doesn't matter. Pick their birthday and take a look. See what you find. You never know. Could be something really cool. Could be a video. Could be audio. Sometimes there's just audio files on here. Anyway. Next topic of discussion. Again, if you are new to the channel, please be sure to like and subscribe. This is kind of a free-form thing. We do talk about the sky the way it is at night. We'll get to that in just a little bit. We usually start off with kind of just general news stuff, talk about things. It's always good to ask questions. If you have any questions, just post them in chat. We are live on Facebook and Twitter. Twitch. See, we're live. That's why I screwed up. We're live on YouTube, we're live on Twitch, and we're live on Facebook all at the same time. I do have a multi-chat stream on my side of things. You can't see it, but I can. So feel free to ask questions. I'm happy to stop and try to answer them the best I can. But the one topic I did want to talk about before we go any further is this. Yuri Gagarin. Now, this is not some, tanky USSR kind of thing, but Yuri Gagarin was a Soviet pilot, and he became a cosmonaut, and he was the first human to go around the planet Earth. Now, of course, the Soviets won the early space race by getting a satellite up with Sputnik, and then, of course, they sent up dogs, and they sent up, monkeys and things like that. Laika, unfortunately, did not make it back to the Earth, and that poor little puppy. But Gagarin actually did went around the planet, and then came back down, received, the Hero of the Soviet Union medal and all that kind of stuff. And even to this day, people still talk about Yuri Gagarin. For whatever reason, the KHL, the Continental Hockey League, the Russian Hockey League that replaced the Russian Super League, their cup is not called the Stanley Cup like we have in the United States and Canada with the NHL, the Lord Stanley's Cup. Theirs is called the Gagarin Cup. It's named after him. He's that big of a deal. So why am I talking about this? Well, that one time that he went around in Vostok 1 was on April 12th. That's today. 1961. Today's 2021, so it's been, 60 years since this happened? Lots changed in 60 years, right? That was just to get one man to orbit around the planet. Now we've got satellites, now we've got GPS, got plans on flying a helicopter drone on the planet Mars. We got, plans to build moon bases. A lot's changed in 60 years. If you've never seen what he went around the planet in, that looks terrifying. But that's what the capsule apparently was supposed to look like. That's kind of a graphic of it. That does not look safe. Doesn't look comfortable. Doesn't look safe. Doesn't look safe. But hey, early tech. That's the way it went. You were there. He is, dashing young man. The missions to get people into space didn't always go well early on. Many people did die, both in the Soviet Union and the United States. Space is hard. But I did want to start out with this and at least mention it because it is important. It doesn't matter what country, and I don't want to get all socio-political or talk about geopolitics or whatever. And if you want to talk about that kind of stuff, go find Vaush. He's over on Twitch. Actually, he's streaming right now as well. That's probably why no one's here. No one cares about me anyway. But you can hear him arguing with Marxist-Leninists and all that kind of stuff. But anyway, we're talking about Vostok 1. This is, again, what it looked like. It was launched at the Baikonur Cosmodrome, as it's called. That's in Kazakhstan. That still exists. That's where the Soviet Union launched stuff from. That's where the Russians still launch stuff from. believe they lease the land. Unfortunately, some of the storage units there have failed and destroyed the Soviet space shuttle, which was a drone long ago. A couple of them are still there, and one of them got crushed by a hanger falling down on it. I did find in my search... Oh, God! Let's mute that. I actually found video of the launch for whatever posterity this is. Obviously, it's not going to look very good because we have, you know, 1080p and 4K and stuff nowadays. But this is the launch of Yuri Gagarin into space. And again, I don't care what country you come from or what the politics are. I'm here about space. And so we got to talk about the Soviet space program, getting a man to space. Briefly, we'll look at this, and then we'll get into talking about what you can see tonight. All I see is blurriness. I apologize if it doesn't look too good on your screen, but it looks terrible on my screen too, so there it is. There's the heavy lift. I will admit Soviet heavy lift rockets looked really cool, and, you know, the modernized Russian ones, they just physically look like cool designs. They may not be the best designs, they just look cool. And again, no one was really sure how this was going to go. You know, some dogs made it back, some didn't. With the NASA program, you know, some monkeys made it back, some didn't. Oh, this is a cute little animation, isn't it? Look at him go! What I really need to do one day is I need to, like, when I do my videos that are pre-recorded, I need to change the sound, and when I do a phase change from like one topic to the next, and I put up the little placeholder, you know, saying like, you know, now, you know, the next topic, the little title screen, title card, that thing, title card, that's the word I'm looking for. When that happens, I need to play like the little tone or something of Sputnik. That'd be kind of fun. But yeah, everybody was super happy, and that, you know, they were proven that they had the technology to do that sort of thing. And of course, in the United States, people got really, really scared, and that made more money funnel into NASA because we couldn't let them win. Anyway, that's all that. But again, 60 years ago, that's a really cool accomplishment, and some people probably don't even remember or know. So if that's the first time you've ever heard about that, there you go, Yuri Gagarin. Go look him up. Lots of really cool things named... Oh, God. Lots of cool things named after him. That's not what I wanted to turn Stellarium back. Let's look at Stellarium. Now, this is Stellarium. This is our observing position. This is a planetarium based around where I am, which is here in New Mexico. So your sky may look slightly different depending on your latitude, your altitude from the equator of the planet Earth. We are facing south, and of course the sun is out. And that is this ball right here. Now, the sun, of course, rises in the east and sets in the west, so if you can track the sun in the sky, that at least lets you know which direction you are facing. Now, obviously, you do not want to stare at the sun. Please don't stare at the sun. Don't, especially during eclipses, don't stare at the sun. Don't point up at it. That's how you damage your eyes. If you want to look at the sun, there's two ways of doing it. Well, there's three ways. One, you can spend the money and get filters to look at the sun. Or, because there are some filters you can get to look at the sun, or you can use this planetarium software. Again, this is called Stellarium, stellarium.org. You can download this for free and follow along, or just, you know, screw around in your own time. Here's a good look at the sun. I want to stare directly at the sun for 5 days. Oh, God, you don't want to do that. That would be really, really bad. Now, you don't want to... So someone in chat said they want to stare at the sun for 5 days. I know who that someone is. I'm just not going to say it. Come on, you know that. I know you're just joking. You can stare at the sun through this program or through an observatory that already is set up for it. Thank you for that, because guess what? We're going to stare at something that stares at the sun. This right here is what the sun looks like in our software. That is not exactly what the sun looks like. And by that, I mean, That's not truly accurate. If you want to be accurate, you really want to use a different software, and by software I really just mean your web browser. If you go over to your web browser and you type in Solar and Heliospheric Observatory, or SOHO. Now, SOHO is a, if you're a New Yorker, there is a neighborhood called Soho, but this is not that neighborhood. This is the Solar and Heliospheric Observatory. This is a telescope that is actually between the Earth and the Sun. And its job is to stare at the Sun for days on end, because it can do that. It's actually built for that. Here is the actual Sun, the way it is outside right now. And we're going to look at it in different ways. This is what we would call just a regular image of the Sun with some sunspots. Now, what is a sunspot? Hold on. There's a lot of things to cover here. First off, let's look at scale. We got Jupiter, this circle down here. We got Earth, which is about the size of my mouse. Okay? My pointer. If you really pay attention, these sunspots are about the size of the Earth. This gives you an idea of scale of how big the Sun itself is. Also of interest, if you really pay attention, you can kind of look through the edge of the Sun. The Sun is not solid. The Sun is a ball of hydrogen gas and plasma. There's actually other gases mixed in there as well. And it's very, very active. It has a core that is fusing hydrogen into helium. It is what we consider the kind of the yardstick. It's what we measure other stars by. Again, we're still on the Solar and Heliospheric website, Solar and Heliospheric Observatory website. Here's kind of what you would expect the Sun to look like, kind of a yellowish colored star. There again, you see the sunspots, again Earth-sized, because they're about the size of my mouse on the left-hand side of your screen here. But what if we use different methods of looking at the Sun? What if we can look at the magnetism? What is a magnet? Magnets, how do they work? I am not going to sing that song because I'm not singing Insane Clown Posse on stream. That sounds like a terrible idea. I agree, Sirius. Here we are looking at a magnetic image of the Sun. Remember where the sunspots were? What do we see? You see, likely negative is dark and positive is the white, or you can do it the other way around. Doesn't matter. You see two different colors, which means there's two different magnetic fields. So what does this tell us about sunspots? Are sunspots magnetic? Yeah, there's something going on there, right? Turns out sunspots are highly magnetic regions, and because of the way they work, they prevent material from bubbling up to the surface, and then, well, material bubbles up to the surface of the Sun, releases sunlight, and then it cools off and then returns back in. It's a process of convection. Well, where these magnetic fields are really, really twisted up, you get a sunspot. The temperature goes down. Sunspots are darker. They are cooler than the rest of the Sun. There's the sunspot right here. You see, this is magnetic activity. This is actually looking at ultraviolet. This is images that our eyes can't see. This is above what our eyes can see. And you see, regardless of which color we use, we see activity around sunspots. Now, that activity usually is going to be solar filaments, so little bits of material kind of sticking up from the surface, and you can actually kind of see that over here. You see it on this side. The Sun looks like it's got a bad hair day. But again, look at where the sunspot is. Look at the literal magnetic field lines pulling material from one section of the Sun to the other. Now, let's look at it in probably what's hydrogen alpha. Yeah, let's take a look at this. Yeah, there's that sunspot again, isn't it? But what do you now see? We see all this material coming up. So there's a couple of things outside the surface of the Sun. First is what's called the corona. The corona is kind of the atmosphere of the Sun itself. It reaches out away from the Sun. And there are sometimes huge explosions, what we call coronal mass ejections. This image from SOHO actually zooms out. The Sun itself is the white circle, but you see a black circle. That circle is actually a cover blocking out the Sun so we can see all the material blowing off the surface. There's probably a comet or some sort of dust going by. Sometimes you see planets or comets in the background of these images. But what do we see here? We see material blowing out from the sun. Now, remember, the white circle is the sun itself. How far out is this stretching? They're talking about like twice the size of the sun. This stuff shooting out. If it's off to the edges, it just looks cool for us. If it's coming towards us, that could be bad. Let's zoom out a little bit. Now, here we go. This is a great picture. So again, same idea, the dark circle, a blocker. The white circle is the sun. This little black line, that's the arm holding onto the blocker. We got the planet Mercury off on the right-hand side, Mercury. And we got Venus right over here. Right over here to the left. That's dumb. To the left, you see Venus. You see, again, material kind of floating around in space. And what do we see here? We see this weird twist. This is a coronal mass ejection. We got material being blown off into space. And again, the sun is right here, so this is 2-3 times the width of the sun being blown out in all directions. Not always all the time. Sometimes it's off just to the left or just to the right. If it comes towards us, that's where we have to panic a little bit, and you'll see activity in the upper atmosphere of the planet on the north and south poles of our planet. That's what causes the aurora borealis. So the more of that hits us, the more active the northern and southern lights are, and the more interference we get with our radios, the more interesting problems can occur. Again, just depending on how active the sun is. Now, the sun itself, again, goes through cycles. It's 11 years from maximum to minimum, so a total of 22 years, going from solar maximum to solar minimum. Kind of gives you an idea of how active or how quiet the sun can be. We are actually just leaving solar minimum, so for the next 10 to 11 years, the sun will be getting more and more active. So if you see a show next year, instead of just having a couple of sunspots, we may have huge areas of sunspot activity on the surface of the sun. And again, you can see here, going from 1996 all the way through what looks like a really quiet phase, and then very active again. Really, really cool. Our sun is incredible to study. If you've never read about the sun, again, I invite you to visit Soho and then kind of go down the rabbit hole of studying the sun. I had the fortunate occurrence to opportunity, I should say, to be able to run a solar observatory when I was at the planetarium. And so every Sunday I got to stare at the sun through filters and talk about the sun and teach people, and it sure almost killed me, that's for sure, because it gets hot in observatories. And if you've never been to New Mexico in the summer, July and August, if you're inside of a big metal box, you're talking 110, 120 degrees Fahrenheit all the time, and it can give you heat stroke. So the sun's an incredible thing to study, but it can be very dangerous. Please don't stare at the sun. We're going to let the sun set in the western sky now. During the daytime, you'll notice blue sky. Assuming you're in a nice area where there's no pollution in the air, the sky is blue. That is, again, think about the rainbow, Roy G. Biv. Let's take a quick peek at that. Again, this is why this planetarium works, because we can kind of jump around to different ideas. I should have had this up. I apologize. Let's take a look at this. Let's get it up first, and then we'll talk about it. There we go. Let's dump this. Let's go over here. So, when you talk about the color of the sky is blue during the daytime. During the morning when the sun is rising, and during the evening when the sun is setting, red wavelengths get through, and so you get the reds and oranges and make that beautiful sunrise and that beautiful sunset color. Now, that is a very narrow band that our eyes have evolved to see. Red, orange, yellow, green, blue, indigo, and violet. That is the visual light spectrum. But when we talk about astronomy, we have to talk about everything. So we have to talk about radio waves. Radio waves do get through the Earth's atmosphere from space. These are huge wavelengths of light. I know you hear radio when you listen to a radio, but it's also a form of light. This is the electromagnetic spectrum. This is light in various forms. Radio waves are a form of light. And you have very, building-sized frequencies at that point. Then you have human-sized ones. So between radio and microwave, they're like human-sized waves. After you go through microwave, you get to infrared. That's, again, below. All of these are below what we can see. Infrared, very small. You talk about heat. You can sense heat. You know, FLIR cameras look at heat. Invisible light, that's what we can see. Everything above what we can see is called ultraviolet. Why? Because the last bit we can see, red, orange, yellow, green, blue, indigo, violet. Ultraviolet meaning above, or, you know, superior, above that. Ultraviolet light. Then X-ray and gamma ray. X-rays you've probably heard of when you go to the hospital. They take an X-ray of your bones if you broke something. Gamma rays you get from nuclear explosions or nuclear fission in the case of stars. Gamma rays do float around in space after stars explode or around black holes. Those don't get through our atmosphere. So all of these that have a big N up top, so gamma, X-ray, and ultraviolet, don't filter through our atmosphere very well at all. So you have to have observatories in space to see them. Visible light does make it through. Some infrared does. Microwaves don't. Radio waves do. Just the way our atmosphere is, the way the Van Allen belts, the magnetic radiation belts around our planet are, that's just the way it is. So if you want to build a microwave receiver or ultraviolet, X-ray, or gamma ray receiver to take pictures of the sky, they have to be in space. Visible light, some infrared, and of course radio waves. You can actually have those observatories on the planet Earth. So, you know, big telescopes for visible light, radio observatories like the now deceased Arecibo Radio Observatory in Puerto Rico, the Very Large Array here in New Mexico, and I believe there's one in China now that's slightly bigger than the VLA, or slightly bigger than Arecibo. In any case, that's what's going on with light waves, and that's why when you look at the sky, during the daytime it is a nice bright blue, during the evening it's a nice orangey red or a yellow, depending on your position on the planet Earth. Now you'll see really closely it says the moon is right on the horizon, so you're not going to be able to see the moon tonight. The moon is our only natural satellite orbiting around the planet Earth, and it goes through phases. Right now the moon is in what's called new moon phase. It's in the sky at the same time as the sun, which means you don't get to see it at night, so that doesn't really help us with our planetarium show, does it? So we're gonna have to cheat. Let's go to our other software. Let's go to Universe Sandbox, or Sandbox Universe, however you want to call it. First off, let's get a good quick peek at the sun, since that's what we were talking about earlier. Here you can see the convection zones actively bubbling up. Just wanted to kind of zoom in on that since we were talking about the sun earlier. But there's the sun in the middle of our solar system. We'll get back to the solar system structure in just a little bit. Just wanted to kind of show off a little bit of what's to come. This is Universe Sandbox. You can actually buy this on Steam. It is considered a video game. It's mostly accurate for the most part. There are some inconsistencies, but that's okay. We're going to use it as best we can to teach. I actually learned about this because a friend of mine said, hey, Markiplier's playing a thing, and he's blowing up planets and stars. You might like it. And that's this software, but I'm going to use it for teaching instead of blowing up stuff. We'll blow up stuff later anyway. So, before we get to the moon, let's look at the Earth at night. This is the reason why you can't always see the sky looking very beautiful, because, well, there's a thing called light pollution. Wherever you see bright spots on this globe at night, that's where a lot of people are living. That's where there's a lot of city light. And, well, you don't see the sky the way it's meant to be seen. Pick out your favorite big city. You can see India there, you see Cairo and the Nile River, you see Madrid, you see Paris, London, there's New York and Los Angeles. Yeah, so bright light's bad, no light's good. Earth in its orbit around the sun does have this beautiful companion, moon, right here. Here we go, let's look at the moon. This is the only side of the moon you will ever see, because the moon is what's called tidally locked. There are pictures of the backside of the moon. Satellites have flown back there, and of course, humans have as well, in spacecraft. But you, living on the Earth, will not see the backside of the moon because of that tidally locked orbit, which means this face is always looking towards us. That said, as the moon orbits around the planet Earth, it does actually get sunlight on the backside of the moon. Of course, the old Pink Floyd album, Dark Side of the Moon. There is not truly a dark side of the moon. There are dark areas on the surface. These dark areas were called seas or mare. They were lava fields that eventually solidified. They are the younger areas of the moon. You'll notice there are some impact craters in these areas, but not as many as in the highlands of the moon. This is actually the backside of the moon coming around as we orbit around the planet Earth. Instead of being tidally locked, we're going to look at the backside of the moon. Again, you see huge cratering. You do see some mare on the backside of the moon, but not as much as you do on the front side of the moon, the side facing the Earth. This side's slightly thinner because the Earth's gravity's been pulling on it for a very long time and has actually pulled some of the material towards the Earth. So it's not fully spherical. It's a little bit more stretched out on the Earth-facing side, letting all that lava kind of flow out. There's the backside of the moon. So this is actually where the moon is in its phase right now. So you see the Earth. Where is the Earth? Oh god, I've lost the Earth. There it is. 3D space, got to think about that. So there's the Earth in the background there. And you see all the lights bouncing off the backside of the moon. So in 3 dimensions, that's actually what's going on. The backside of the moon's getting all the light. From here on the Earth, what do we see? Nothing. And then, as the moon goes around in its orbit, it'll start to reflect sunlight back towards us, and so we'll start to see a crescent moon appear in the sky. Now, the word month is based around the moon itself. The moon orbits around the Earth every 29 Earth days or so. The month itself does not always line up with the calendar month, and so the months can be a little bit wonky where you have different phases starting out the month. Here's that little moon phase diagram that we saw a little bit earlier. This is the phase we're in right now, new moon, so sun and moon in the sky at the same time. As the moon orbits around the Earth, you see its angle changing. You see the moon getting brighter on the right-hand side. So for the rest of this week, you're going to see the moon appearing just after sunset in the... Well, it's going to be out actually just after sunrise, but you'll see it very, very brightly as a crescent moon along the horizon, and then it'll go down past the horizon just about an hour or so after sunset. There's first quarter. It's gone 1/4 of the way around our planet Earth. If you haven't done so, hydrate, eat your snacks. Don't forget to snack. Don't forget to hydrate. After the crescent phase, you have what's called a gibbous phase. So it's not full, but it's not a crescent either. And then you get to what's called full moon phase. Full moon and new moon are opposite of each other. So right now we're in new moon phase. So in 2 weeks, we'll get a full moon. Full moon is when the sun sets and the moon rises at the exact same time because they're opposite of each other in the sky. Turn back on. Turn back on. Thank you. Now the phases go in reverse now. You go waning now. Instead of waxing, it's now waning. Waning gibbous into a waning crescent. So waning gibbous going into a third quarter moon. Now these you're going to see really, really late at night or early, right before sunrise. And then the moon will get quote-unquote smaller and smaller and smaller in the waning crescent phases until we get back to new moon phase. That's what's going on, the moon orbiting around the Earth. This diagram has us looking directly at the North Pole of the planet Earth. You see us going around on our daily trek, and the moon slowly going around. So, what does this all mean? Think about this logically now. How long is a day on the moon? A day on the Earth is 24 hours. A day on the moon is 2 Earth weeks long. Think about that. If you lived on the moon, where that pink dot is right there, boom, you're now hitting sunrise. On the moon, you live on this pink dot. It's now sunrise, the sun is rising up. And the sun will keep rising up until you get to sunset, right? And that's when you get into that other phase where the dark spot, the darker Side's on the right-hand side, so keep an eye on this. How long has this been? It hit it here, and we were here, so it's been a week, and now we're waiting another week, aren't we? So a day on the moon is 2 Earth weeks, which means night on the moon is also 2 Earth weeks. Because this would be sunset when this dark line hits the Terminator, as it's called, once again hits the pink dot. There's sunset. Sunrise was at first quarter, sunset going to be at third quarter. So now you have 2 weeks in darkness. So what does that mean? If you live on the moon, how is that going to work? How are your days going to be structured? Could you imagine sleeping for a day on the moon? That'd be 2 Earth weeks. That'd be amazing. Catch up on all that sleep you've missed out on. But these are the things you have to start thinking about. What if you have a colony on the moon? You have a little moon base, you got people working there. That means that you have to have some sort of rhythm, circadian rhythm thing in their room so they can sleep, or that they feel they're in daytime or nighttime. Maybe they get to look out when it's daytime and they, artificially put light into the window to make it look like it's daytime when it's really not. I don't know. But think about that. A day on the moon is 2 Earth weeks long. Night on the moon is 2 Earth weeks long. The full orbit is 1 full day, going from day to night to day again on the moon. That's a whole month here on the Earth. Conversely, that means, there's 365 Earth days. How many days are there on the moon? There's only 12 months, right? So if you were born on the moon, you really would be only 12 days old after a whole Earth year. Freaky. Things to think about when you talk about people living on other planets or other celestial bodies, in this case, the moon. Yeah, I know, it's a weird thing to think about. I apologize. Sort of. So that's why there's no moon out tonight. What do we have out tonight? Well, we have a lot of these things, what are called stars. The word star comes from asteros. This is a Greek root word. I feel like I'm watching my big fat Greek wedding. It comes from Greek. Planetes asteros and asteros. Asteros meaning stars. Planetes asteros meaning wandering star or vagabond star. Objects that move through the sky. Because you see, there are fixed stars, what we call fixed stars. These stars are always in the same exact patterns. They change with the seasons, but the shape of the pattern remains the same. These fixed stars. So they were grouped up into different things. Constellations, we call them nowadays. A lot of these constellations have been around forever. There's actually a thing called the Dendera calendar? Dendera? Yeah. Let's look at this thing real fast. This is called the Dendera Zodiac. It is something I want to see in person, but I know I can't because it's very far away. It originally was in Egypt. Okay? But because of the way things work, it was literally sawed out of the roof of the Temple of Hathor, and it was taken to France. It's in the Louvre at the moment. This is the modern representation of that particular sky. This is the actual Dendera Zodiac in the Louvre. And what it shows, what it represents, are constellations. These have been around since ancient Greece and ancient Rome. But in particular, this one, these are ancient Egyptian constellations. And you see a lot of the same ones that we still talk about today. You see here, there's Leo the Lion, as we call it. Come on, Leo the Lion. We got Virgo. We got, all these different shapes. What we call the Ursa Major and Ursa Minor, the big and little bear, in their sky chart, they were actually jackals. This is a colorized representation of it. I can't zoom in anymore. I apologize. But look at the constellation shapes. These are very similar to what we have today. There's Orion very clearly right up here. I can't zoom in anymore. I apologize. Orion's right here. The V shape, that's Taurus, the bull. This right here is what we would call the Pisces fish. Let's see, just twisting my head. There's Capricorn right there. This right here is Scorpius. This right here is Ophiuchus. These constellations have been around since ancient Egypt. We see them on our planetarium dome back here. Well, those like Ophiuchus and all that, that's not going to be up till later. I'm going to zoom through the constellations here just to show you. Those are the exact same shapes. You see this right here with the snake-looking thing up front and this weird shape right there? Let's go back to the other thing. Come on. It's right here. There's that. There's the snake shape up front. There's a J of stars below it. Well, look at that. There's a J of stars right here on our planetarium dome. These are ancient constellations. These constellations that are on that Dendera Zodiac, those are Egyptian, but they likely got it from the Sumerians in Mesopotamia. There's Sumer, there's Assyria. A lot of these constellations are ancient things, and we still talk about them. There are 12 of them that are very, very distinctly important to people. Now, we'll talk about those in a second. I just want to point out that these are, again, based on Greek and Roman legends now, but these go back to ancient Egypt and likely further back. But since there are other cultures on this planet, there are other star lore. Let's look at Chinese, just to show a vastly different sky. It's the same set of stars, but the constellations are different, so the stories are different. There's different stories in India. There's different stories in Navajo here in the United States, here in New Mexico. The Navajo stories. The Diné people, they have their own constellations. This is not a complete list of them, obviously, but they have their own constellations. This is all the same exact section of sky. And this is why I love astronomy, is because it doesn't matter where you are on the planet. Even if you're in the southern hemisphere, the constellations are different, but they still have constellations. Those stars, the fixed stars as we call them, have always been in the same spots. Depending on the season, you see different shapes in the sky. The stories may be different, or maybe they're the same, just with names changed. Here we go. But there are 12 particular ones that we call the Zodiac constellations. The Dendera one talks about the Zodiac as well. These 12 constellations, think about how the calendar is set up. We've got 12 months in the year, and there's 12 Zodiac constellations. There are 7 Asteris planetes, planets. Now, okay, I gotta explain this real fast. The Greeks and the Romans, starting with the Greeks, they called them wandering stars, wandering planets. They considered the sun and the moon to be planets. Obviously, today we call the moon a satellite, or the moon. The sun is a star. But there were 5 other objects, Mercury, Venus, Mars, Jupiter, and Saturn, as we know them today, that you could see without a telescope, even way back then. Those 7 total objects, the sun, the moon, and Mercury, Venus, Mars, Jupiter, and Saturn, were called the 7 classical planets, the 7 wandering stars of the sky. They didn't know about Uranus and Neptune till later. There's 7 days of the week. Again, look at your calendar, 7 days of the week. Each day represents one of these 7 objects. Sun, Sunday. Monday is the moon. Tuesday, if you speak Spanish, you would know. Martes is Tuesday. Any Romance language, any Roman-based language is going to call Tuesday Martes, or some variant of that, which means Mars. Wednesday is going to be Miércoles, Mercury, Miércoles, Wednesday. Thursday, Jueves, Jupiter, Júpiter. Thursday. Friday, Viernes, Venus. Friday's Venus's day. Saturn, Saturn's day. The days of the week represent the 7 classical planets. The months of the year depend on where the sun is in the sky, and they all happen to travel on this nice little band, what we call the zodiac. It's also called the plane of the ecliptic. You've probably heard many of these, so just kind of zooming through, we got Taurus the Bull, we got Gemini twins, Cancer the Crab, Leo the Lion, Virgo, Libra the Scales, Scorpius, Sagittarius, Capricorn. Again, these were all on that Dendera Zodiac. The sun is now up, so you don't see it very well. Let's get rid of the sun. Capricorn's here. Aquarius the water bearer, even though it's an air sign somehow in astrology. Don't ask me. Pisces the fish. Aries the ram, and then back to Taurus the bull. And you see right now the sun sits in Pisces. This is how the calendar was built. You know, if the sun is in Pisces at night, you know exactly which stars are going to be up because you've kept track of the sky. And so you know if the sun is in Pisces and when the sun sets, that means that you'll have Taurus the bull and all these other constellations out at night. So by just observing the sky, you know exactly where things are and what season, besides the fact that, you know, it's hotter or colder in the day or at night, you know what season you're in if you can tell which stars are up, which constellations are up. Now, that plane of the ecliptic is better seen if we go to Universe Sandbox. Remember this? I told you we'd be back to it. Remember me, Eddie, when I killed your brother? That's a Roger Rabbit reference, doesn't matter. There's the sun. As we zoom out, you'll notice all the planets appear to be kind of on a flattened out plane. The plane of the ecliptic. If you were to draw these lines out all the way, you would see the zodiac constellations along these flattened out lines. How does this work physically? Well, think about pizza. If you've ever made your own pizza or if you've watched someone make a pizza, what do? They make a little ball of dough. They mash it all together, make sure it's nice and uniform. They let it rise a little bit, and then they start to spin it. And as it spins, what does it do? Well, pizza's not round unless you're eating a calzone. As it spins out, it starts to flatten out. It's the same idea. There was a huge cloud of gas and dust long ago that started coalescing, and that cloud coalesced and formed the sun. But with that, there was some heavier material. Now, normally when a star is formed, it forms from a hydrogen cloud. So the star itself is made of hydrogen, and then as it fuses different things in its core, it gets older. We'll talk about stars' life and death in a little bit, but bear with me. When that star dies, it then throws all of its elements out into space, making new clouds, and from those new clouds, new stars will form. They will have heavier elements in them and around them. The first 4 worlds of our solar system are rocky. They are heavier element worlds, which implies that our solar system is recycled material from a previously born and deceased star. Heavier elements like carbon and neon and iron. Iron, like the iron in your blood, the stardust that resides within you. You, my friends, are stardust. That stardust also helped form other worlds, such as Mercury, which we'll take a look at now. Here's Mercury, small rocky world. Kind of looks like the moon, but darker. It is considered to be sun-scorched. It is burned a little bit, so to speak. No atmosphere, very hard to see, because it's so close to the sun. You don't get to see it very often at night or in the morning. You see it briefly for a week or two, and then it's gone. Named after the messenger god of Roman mythology, Hermes in Greek, Mercury in Roman. Next planet out is the morning star or the evening star Venus. Obviously not a star, it is a planet. It's like Earth-sized, give or take, but that's about where the comparisons end. Some people call it Earth's evil twin. It rotates the wrong way. Sun rises in the west and sets in the east on Venus. Don't know why, no one's really sure. It's also a very slow rotation. You know, we have a 24-hour day here on the Earth. On Venus, that's approaching 220 Earth days, I believe it is. I'd have to double check. It might be 242. One of those numbers is sticking out in my head. Anyway, it rotates very, very slow, so the sun is always kind of up in the sky and it just slowly rotates. No one's really sure why Venus has that rotation issue. It's one of the mysteries of our solar system. There's the Earth once again, and I believe we can actually add the moon in. Is that a thing we can do? I know there is a way to do this, but add moon. There we go. There's the Earth and the moon in the solar system. There we go. We've talked a little bit about the Earth, so let's skip Earth and go to Mars. Obviously, we started talking about the Mars Exploration Rover missions, and we started talking about the Mars Perseverance mission. Let me slow this down a little bit so we can watch Mars rotate. Mars has an Earth-like day. It's 24 hours and 37 minutes long. Mars has seasons. It has ice caps made of dry ice, carbon dioxide ice, frozen at the North and South Pole. They melt and get bigger and smaller as things go along. There's a huge crevice along the surface called Valles Marineris, which we just saw go by. That is a crevice that's about 8 kilometers deep, 5 miles deep, and it would stretch across the United States. It would go from San Francisco all the way to New York City. It is a huge crevice along the surface. The assumption is that the planet actually cooled off and the interior dynamo just kind of screwed everything up. Oh god, that's not what I wanted. It cooled off and then cracked on the surface. Go back to Mars. There we go. Mars does have 2 satellites orbiting around it. One is called Phobos, named Fear. The other one is called Deimos, named Panic. It's very strange to see it labeled like this. Those are their names. Phobos and Deimos, if you look at them up close, they are captured asteroids from the asteroid belt, which is not too far from the planet Mars. Let's look at Deimos real fast. You can see very, very heavily cratered. The asteroid belt is filled with kind of leftover material. There's not really enough to make a full planet there. Some people think there may have been a planet there, but it doesn't seem to be the case. Let's take a look at just, some of these little planetoids. They are, for the most part, solid objects. Some of them are considered to be kind of like clumped together chunks of other objects. Most of them are spherical. Some of them are going to be potato-shaped asteroids. When you think about an asteroid, you're probably thinking of a potato-shaped asteroid kind of tumbling through space, because that's what sometimes happens. Some of these are named because they are considered minor planets or dwarf planets, like that. Would like to invite you to think about, well, what about mineral rights? What do I mean by that? What if there's like silver or gold or iron, lots of iron on some of these asteroids? Could we go out there and mine it? It'd be expensive now, but in the future, could we go out there and mine asteroids for minerals? Why not? Let's go past the asteroid belt. So again, the asteroid belt between, there's Mars right there, the red stripe. All these little asteroids out here, they're in a huge field, and they're not just in a flattened out plane. They kind of go in all directions like a little bubble around the sun. Then you enter into the gas giant realm. So the gas giants look something like this, and you'll see they rotate very, very fast. This is Jupiter. This is the king of the planets. King of the Roman gods. This is Zeus in Greek. There's a huge spot called the Great Red Spot in the upper atmosphere. It's about 4 times the size of the Earth. It's a huge storm that just keeps raging on. The first time it was seen was in the year 1610 by Galileo Galilei, and it's still there. So, just doesn't seem to want to go away anytime soon. Jupiter, there's the red spot, has a lot of moons. A lot of moons. You can kind of see their names have appeared in the simulation here. So we've got Io, Europa, Ganymede, and Callisto. Those are the 4 that you can see through a telescope when you look at Jupiter. Io, can I zoom in on Io? Will it let me go to Io? Come on. Come on. Io is a small volcanic world. It is too close to the planet Jupiter, and so it is being literally shredded apart by Jupiter's gravity. There's actually active volcanoes on the surface, and so the surface is not the way it looked when it was first visited by various probes like Voyager 1 and Voyager 2 and things like that. This is Europa. You'll probably remember Europa from the 2001 movie. 2001: A Space Odyssey. They talk about Europa. It is an ice moon. Very intriguing little moon. You see cracks on its surface. And it is assumed that after about 10 miles, or, 22 kilometers, give or take, of icy crust, that there is liquid water under the surface of this moon. Because of its proximity to the planet Jupiter, it's actually being pulled back and forth, and that back and forth pulling is melting the ice. There's likely a saltwater ocean under the surface of Europa. Here's Ganymede, the largest moon in the solar system. This is about the size of the planet Mercury, and it's orbiting around Jupiter. Also an icy world. There it is. There's Callisto. That's the last of the Galilean moons, the ones you can see through a telescope when you look at Jupiter. There's a huge number of moons. We're not going to go over all of them. I finally figured out how to add these in. You'll notice, look at their names. Look at them. Look at how far out they all are. These are all in gravitational orbit around Jupiter. Some of them are likely captured asteroids, or they may have been comets that never truly lit up and they kind of died over time. Comets usually have a lot of ice on them, so if the ice sublimated and turned into gas, now they're just like a core floating around, in this case, Jupiter. Very, very cool. Let's go to Saturn. Now, Saturn has been the bane of my existence in this software because when you get to Saturn, it looks like this. There are no rings around Saturn in the simulation, but in reality, Jupiter, Saturn, Uranus, and Neptune all have rings. I have moons here now, but I still don't have rings. As it turns out, that is my own fault. I have to click on a little thing. It's supposed to add in the rings. Maybe? Did you do the thing? Oh, for God's sake. Scree! You can kind of see them. There they are. You see a very, very thin pattern of rings, but that's still not very good, in my opinion. You might not be able to see it on the stream. There we go. You can kind of see there's a little line right here. Let me zoom in a little bit. You can kind of see there's a very thin line of particles. They are not solid. They are, of course, made of ice and rocks. And so Saturn's rings in this simulation, again, they're not reflecting back what you would expect to see when you look at Saturn. When you think of Saturn, you probably think of, let's get a picture up. When you think of Saturn, you probably think of something like this. Ba-ba-da-ba-da-ba-da-ba-da. Come on. Let's get a picture of Saturn up. While I work on that, I'll talk about Saturn. So Saturn has rings. All the gas giants do, but Saturn's rings are the most prevalent and the easiest ones you can see from the planet Earth. Saturn does have a large number of moons. I believe the number is 82 satellites orbiting around the planet Saturn right now. There we go. That's likely what you think of when you look at Saturn. We see all this light reflecting off the surface of these little icy particles. This is likely the result of an ice moon or some sort of large comet being shredded by Saturn's gravity and then being caught in orbit. The rings themselves have little moons inside of them. They're called shepherd moons. They orbit within the rings themselves. You see moons all along the edges of the rings, and you see a moon hanging out here. We'll look at Titan, which is that moon right there. We'll look at it when we go back to the other software, but I just wanted to look at Saturn. This is my personal favorite planet. This is the reason I became an astronomer. I try to use Saturn as a logo in most everything. My first business card had a Saturn in the background of it. It's just such a pretty planet. Can't say enough about it. I just like it, okay? But yes, there are a very thin... There we go. You can kind of see that it's highlighting little particles in the ring system. They just don't look very good in here, and it just ticks me off. You can see all the little moons that are in orbit. There we go. We can kind of see the rings a little bit better as we zoom away. There we go. You see all the little planetoids. These are all moons orbiting around Saturn. I am looking for Titan. I don't see its name. There it is. Titan's back there. Titan is the only moon in the solar system with an atmosphere. This is an atmosphere made of methane. Methane you would call, of course, natural gas here on the Earth. But it's so cold out here, you actually get liquid methane. You get raining methane. There are rivers of methane under this atmosphere. We actually had a probe orbiting around Saturn a few years back called the Cassini probe, named for the same scientist that discovered the Cassini division in the rings. And aboard that mission was a piggyback mission called the Huygens space probe, named for Christian Huygens. And he was also a guy that studied Saturn a lot. And that probe actually pierced the atmosphere and fell down towards the surface. There's actually pictures of this moon from a satellite on its way down, and it took pictures of lakes and rivers, all made of methane. Very, very cool. Speaking of cool, Enceladus. That's the moon I'm looking for now. I see its name. There it is. Remember we talked about Europa? Enceladus is much the same. That is this moon right here. Enceladus has geysers of water spewing from its surface. This moon has liquid water. We know it. And that raises a huge question. If there's liquid water here, could there be life? We don't know. I guess you see the rings a little bit better when you get out here. As you go out, you see these are all in orbit around Saturn. They're all in some sort of stable orbit, so the moons can be very, very far away from the actual planet itself. What's next? After Saturn, you get Uranus. Let's zoom in here. So I'm going to go ahead and assume that I can add rings to Uranus as well. I can. It just takes it a little bit to kind of process them and add them in. The rings are parallel to our standard orbit. Not sure if it's going to do it, but that's okay. As you can see, the moons are along the ring system, so actually, yeah, you can barely see the rings. They are very, very thin rings around this planet, but here's the kicker. You see all the moons? They are on the same plane as the rings. This is the equator of the planet. The planet's tilted over, and we don't know why. Uranus is on its side, its rings are on the side, its moons are on their side, and they all go around the planet in orbit around that same plane. Why is it all on its side? We don't know. That is a huge mystery. Since we don't have orbiters around the outer planets Uranus and Neptune, we don't really know a lot about them. Voyager 1 and Voyager 2 kind of flew by each one, but we don't really know much more than some of the pictures we get from ground-based satellites, or ground-based telescopes, I should say, or from some satellites like the Hubble. Doesn't look like they have Neptune rings, and that's okay. There's a very thin ring system around Neptune. It does have some moons, not a lot of them, but there are some in orbit around the planet. Triton is this moon out here. It orbits around in the wrong direction. The idea here is that it was likely a comet that got captured by Neptune. It travels around the planet in the wrong direction compared to the other moons. Very, very strange little world. And that's the solar system. That's our tour of the solar system. Out here, of course, you get Pluto and Quaoar and Eris and all these what are called trans-Neptunian, so further than Neptune, trans-Neptunian objects. There's what's called the Kuiper Belt, which is where all the comets kind of start coming from, and then the Oort cloud, which is literally just a depository of comets way out here. A huge shell of objects. And that's it. That's our whole solar system. Once you get far enough away, the sun itself just kind of disappears. I still see it labeled, obviously, but from this distance, you can't even really see the sun compared to all this stuff in the background. That's the Milky Way galaxy that we see, and we'll talk about the Milky Way galaxy in just a little bit. That was our tour of the solar system. Yikes. Let's go back to what we can see tonight. Now, there's not too many planets out tonight. The only planet you can see is the planet Mars, hanging low in the western horizon. To find Mars, you must find the constellation Taurus the Bull. To find the constellation Taurus the Bull, you gotta find Orion. Why Orion? Because it's the easiest one to find. Orion is the hunter in the sky. Sometimes he's holding a club and a lion pelt like he is here. Sometimes there's a sword and a shield. Lots of different stories about how Orion got into the sky. Sometimes he was shot by an arrow from Artemis, the moon goddess. Other times he ticked off the goddesses and said he was going to kill all of their creations on the Earth because he wants to kill all the different creatures of the planet Earth. And so one of them sent a scorpion and it stung him in the foot. It represents the constellation Scorpio. That's why the Scorpion and Orion are opposite each other in the sky. But here's the thing. Remember I said this existed on the Dendera Zodiac. And so Orion's an old constellation. In some Egyptian mythologies, Orion represents Osiris, the god of the dead. Behind it, you have Sirius, the dog star, but you've also got to look back further. In Egyptian, this would be considered Isis, which is Osiris's wife. Represents the same star. So depends on which mythology you want to look at. Either way, it's still the same part of the sky. If you can find Orion, the 3 stars of the belt, super easy to find. Shoulder stars, Betelgeuse and Bellatrix. Betelgeuse means armpit of the giant. Go figure, it's in his armpit. Rigel and Saiph, his knee stars. Draw a line through the belt stars and you will find a V of stars, the face of Taurus the Bull, and a little patch of stars right above the horizon. Because it's no longer winter, these constellations are not going to be in the sky for very long after sunset. These are mostly seen during the winter. This is the Pleiades, or the Seven Sisters, Subaru, if you want to call them that. Alcyone, my personal favorite star, right there. That is an open star cluster, by the way. Stars come in different clusters. Sometimes they are all born and kind of packed together in what's called a globular cluster. Other times you get loosely kind of floating around stars like this. They are all born around the same time and from the same kind of material cloud, and they kind of float apart from each other. You'll notice our sun is all by itself. Some stars are actually in pairs or triples, so there's 2 or 3 stars orbiting around each other. All just depends on how they were born. This is an open star cluster that you can still see tonight. Later on, we'll be able to see globular clusters. We see them mostly during the summer months, and I'll explain why in just a little bit. But another open star cluster is the face of Taurus the Bull. That's this V of stars. Again, it's going to be right above the western horizon tonight. Aldebaran is the eye of Taurus the Bull. Bright red colored star. We'll talk about the color of stars and what that truly means in just a second. If you can find that V of stars, just draw a line straight up through them and you will find a red object that does not twinkle. Stars will twinkle. Planets do not twinkle. That is the planet Mars, which we talked about a little earlier when we did our tour of the solar system. So that's where Mars is sitting. Now, if you've been paying attention to our shows, if you've been watching our shows or tuning into our live streams, you'll know a few weeks ago we were talking about Mars being right below the Pleiades. Mars has just been slowly drifting through the sky. Again, the plane of the ecliptic kind of tells you where the sun, the moon, and all the planets are going to be loosely. They're going to be along this line sometime. Where? Tune in, you'll find out. Let's use Orion to find the winter triangle. Again, this is seen during the winter months, but we're now in the spring, and you'll notice every night they're going to be getting lower and lower in the horizon, towards the horizon, and so they're leaving the sky. Back to Orion, the 3 stars of the belt. You've got the shoulder star Betelgeuse. Let's see, there's our belt stars. There's our shoulder star Betelgeuse. Draw a line through the belt towards the eastern horizon. You find Isis, or Sirius, once again, the brightest star in the nighttime sky. Seriously, it's really, really bright. We'll look at star brightness in just a second when we go back to our other software, okay? Stay with me. Sirius and Betelgeuse are 2 very, very opposite kinds of stars. Sirius is a bright blue star, very young, very, very hot. Hot, baby. Blue stars tend to be much, much hotter than red stars. They're very, very hot, and I'll show you why in just a little bit. Betelgeuse is what's considered a red giant star. It's a star nearing the end of its lifetime. It has a very distinct reddish-orange glow to it, so that kind of lets you look at the difference in color when it comes to stars. Finally, there's a star named Procyon up here. This is the winter triangle. We've been talking about it for months and months and months. It was first really low in the eastern horizon, and then it was just in the southern part of the sky, and now you'll notice it's really low in the southwest part of the sky, because we're in springtime. Winter is over. Spring is upon us. Night after night, these will be going away to the point where in just a few weeks, we won't see them at all until, September, October. And we'll have to replace that triangle in the sky with another triangle. It's actually one called the Summer Triangle, which we'll talk about in just a little bit. So that is the Winter Triangle. That is made of Procyon in the constellation Canis Minor, the little dog. It's kind of a hot dog, or a dachshund in the sky. It's only 2 stars making that constellation. We got Canis Major, the big dog, and we got Orion with Betelgeuse in his shoulder. Now, back to Zodiac stuff, which I know a lot of people like. Zodiac stuff is usually referring to astrology, which is the, divination and telling futures and stuff like that. Astronomy is something totally different. Astronomy is studying the way things move, the way things form. That's astrophysics as well. Long ago, they were one and the same, but nowadays we do consider them to be separate things. One is a science, one is a belief system, loosely. Above Orion, you find the Gemini twins. To find them, let's get rid of that, and the lines, there we go. Go from Orion's knee star, Rigel, up through Betelgeuse, and just kind of keep going. You end up next to 2 stars. They are parallel to each other. They're right up here. One is named Castor, one is named Pollux. These are the Gemini twins. They're about the same brightness, even though they're slightly different colors. So they look like twins in the sky. So these are the Zodiac stuff on this side of the sky. Cancer the Crab's really hard to see. That scared me. Gary Tran TV, thank you for following. Welcome to the channel. That notification sound always scares me, but I like hearing it, so I appreciate it. Thanks for the follow. Share the channel. We do astronomy stuff. We've been talking about... actually, a lot of stuff. We talked about the solar system itself. We did a little virtual fly-through. We talked about Yuri Gagarin and his historic flight 60 years ago to the day. And now we're talking about just the nighttime sky, so you can find your way around. In fact, let's talk about a zodiac constellation, Leo the Lion, which again was on the Dendera Zodiac. So this goes back to ancient Egypt, if not further. It is a question mark of stars. You can kind of see it up here. We'll zoom in a little bit. You can kind of follow along. Happy Space Day. Yeah, Happy Space Day indeed. This backwards question mark right here, and a triangle shape. Let's draw in the lines. That is Leo the Lion. Now think of the Sphinx, think of Egypt. You can kind of see where we're going. That is supposed to be your lion in the sky. Glad you found us, Gary. Again, we do this Monday and Wednesday and Friday. Friday's mostly news-related stuff. We do live streams whenever NASA does something cool or whenever some of the space agencies do something really cool. We just kind of sit around and watch it and kind of comment on it so as to just kind of take it all in. So in just a few days when they do the, actually on the 14th, so on Wednesday when they do the helicopter flight on Mars, assuming it's actually going to happen that day, we will be here to watch it and talk about it as well, so do follow along for that. We're also on YouTube. We do some pre-recorded stuff on YouTube. We're doing Astronomy 101 content, so be sure to watch that, and of course share it around as I fight with my chair. There we go. So yes, no moon tonight. We did talk about how to find Mars. We're talking about how to find some of these constellations. Let's turn our whole head around. Now remember, the sky itself, there we go, can be broken up into a big grid, okay? To do visual astronomy, you need to be able to kind of gauge distances, and one of the easiest gauges is your fingers. If you have the ability to see your fingers, or move your arms around, because hey, some people don't, let's be honest, I don't want to be ableist here, but if you're able to move your arms around and stuff, put your arms at arm's length, okay? Look at your finger. Your fingertip, your index fingertip, that is about what's considered half a degree. There's 180 degrees from horizon to horizon. Your palm is about 5 degrees, so you can kind of tell how far apart certain things are based on the width of your hand and the width of your finger. A full moon, when the moon is in the sky, full, not now, but in 2 weeks, the full moon is about the size of your fingertip in the sky. May not look like it when it's on the horizon, but you'll notice as it rises up, if you hold your finger out, it's about the size of your fingertip. The stars we're going to talk about here, these are about the width of your palm in the sky, okay? We're going to talk about the Big Dipper. Now, the Big Dipper is not a constellation. The Big Dipper is considered an asterism. It's a shape. A lot of people know it. Some cultures have it as a constellation, but in Greek and Roman, which is what we're basing most of this stuff on, the Big Dipper is part of Ursa Major. That's the big bear at the top of the screen here. The Little Bear, however, is just the Little Dipper. Why the difference? I don't know. I wasn't involved in that decision. I think that's silly. But the Big Dipper is 3 stars of a tail and 4 stars of a cup. Now, the story behind the Big Dipper, again, it depends on the culture. A lot of the Native American stories are kind of interesting, and the Inuit and First Nations up in Canada. Think of this dipper as a big ladle. What happens when you try to get some soup out of a bucket, right? Or soup out of a cauldron? You stick a ladle in, and then you pull it out, right? And how does the spoon look? You're holding onto the handle, and the spoon is kind of vertical, right? It's pointing upwards. Well, what about this dipper? What shape is it? It's kind of like a ladle, 3 stars of the tail, 4 stars of the cup. But it's pointing down. If this were filled with soup, what would it be doing? It'd be pouring down, right? Wait a minute. We're in springtime. Springtime is the rainy season. What if that water is coming from the Big Dipper? In reality, that's not true. The water, of course, comes from condensation and rain. From clouds and, climate and structure of clouds and things like that. But that's a story. When you see the Big Dipper high in the sky like this right at sunset, that means it's springtime. That means the rainy season's coming because the cup is facing downwards. Again, you use the sky, you use what nature is showing you to know whether it's time to plant, whether it's time to harvest, which groupings of stars are in the sky tell you what season you're in. The Big Dipper has 3 stars of the tail, 4 stars of the cup. These last 2 stars right here, we call them the pointer stars because they point to Polaris. Now, these pointer stars are about 5 degrees apart. The width of your palm is 5 degrees, give or take the size of your hand. So if you hold your arm out all the way, these 2 stars should be on one side of your hand and the other side of your hand. So you know you're looking at the right stars and you know about how far apart they are. From your thumb to your pinky, if you have your hand outstretched, that's a good 25 degrees or so in the sky. So you can reach a good portion of the way. And we're actually going to use that here to go find another star. But first, let's find Polaris. These 2 stars, the pointer stars, they point you to Polaris. Simple. Nice and easy. You just draw a line. It's about 35 degrees, so that is about the width of your, if you start here, I should say. That's about the width of your pinky and your thumb. Outstretched all the way, give or take. You will find the North Star. The North Star. Polaris, the pole star. It appears to sit in the sky and not move. All of these stars that are right around it are called circumpolar. They circle the pole. Circumpolar. Convenient. There is a constellation called Cassiopeia, which you can also use to find the North Star. Cassiopeia is a 3 or a W or an M shape. You see it hanging out over here. Gonna get rid of the atmosphere so we can keep seeing these stars. You'll notice, again, they don't go below the horizon. It all depends on where you live. If you live further north, more towards the North Pole, these stars are higher up in the sky. If you live more towards the equator, these stars are lower in the sky. You'll notice where I live, the Big Dipper kind of goes below the horizon a little bit. But Cassiopeia is also in the sky at this point. So they are always opposite each other. Cassiopeia, the queen, and then you got Ursa Major and the Big Dipper as its stomach and tail. They are always opposite of each other. So if you can't find one, find the other. Cassiopeia, because it's made out of 2 triangles, you can use those 2 triangles as arrowheads. Draw a line through each of these as though you were making an arrowhead, and you will find the tail of the Little Dipper, or Ursa Minor, once again. See, it's a little bear right there. There we go. Very, very cool. This is how you find north. So if you can find north, that means east is to your right, west is to your left, south is, of course, behind you. Now, let's use some more of this knowledge. Let's reset to tonight. There we go. We're going to use the Big Dipper to find 2 more stars and 2 more constellations through that. The tail of the Dipper has an arc to it. You see how it kind of arches this way? It arches to a star named Arcturus. Arc to Arcturus. Let's draw a line from this last star here. Follow the arc of the tail, arc to Arcturus. This again is a little bit wider than your hand will be at fully outstretched. Arcturus has a very bright yellowish color to it. And then you can spike towards the south to Spica. Spica is the brightest star in the Slug constellation. Okay, it's not a slug. It's supposed to be a beautiful maiden. It looks like a slug in the sky. But it's supposed to be Virgo, the constellation Virgo. That is Spica. It's bright blue star right there. These are very, very easy to find because they're the brightest things in these portions of the sky. Arc to Arcturus and Spike to Spica. You will hear me say that often because that's a thing you do in the springtime. Because that's when these things start to rise up. Now, I've talked a lot about stars, and I've mentioned their colors, but I haven't really shown you examples of how big some of these things can be. So we should probably do that, right? We should probably talk about them. Let's talk about the stars, shall we? Again, at any point, feel free to stop me with questions or comments. I don't mind, tangential stuff. I mean, about the only limit is I don't want to talk about politics. That's where I kind of draw the line. I don't talk politics here. Just because politics and sometimes music can cause very bad things to be discussed. Let's get a chart up, shall we? There we go. Now let's switch it over so that you guys can see the chart. That's not it. That's not it. There we go. This is what's called the Hertzsprung-Russell diagram. This is the HR diagram. This is what we use to talk about stars. There's a lot of data on here, okay? So let's go at this one at a time. Our sun is considered to be average. We consider its luminosity to be 1. So we compare everything to the sun. Seems logical enough, right? We know the temperature of our sun is about 6,000 degrees Kelvin, about 6,000 degrees Celsius. Celsius and Kelvin are basically interchangeable. Fahrenheit, we're just not going to talk about that because, scientists don't use that, so let's not worry about that. But I guess if you really must know, the surface of the sun's about 10,000 degrees Fahrenheit, give or take. Just using round numbers. Anything to the right of the sun on this chart is going to be down here. You'll notice they are brighter red in color. There's the sun. You'll notice the color has turned red. You'll also notice that it slopes downward. This chart right here has luminosity as the vertical axis, so that means these stars over here are going to be dimmer than the sun. They've also gone to the right. What's on the bottom? Temperature. So dimmer and colder. Now, 2,500 degrees Celsius, 5,000, 6,000 degrees Fahrenheit. For a human, that's really hot. For a star, that's really, really cold, okay? So they're red and cold stars down here. As you progress through the main sequence of stars, which is kind of the linear average of stars, you'll notice that there are some stars that are bigger and brighter than the sun. There's Sirius. Hi, buddy. My dog is named Sirius, so he always looks up when I say his name, when I say the star's name. As you keep going this way, you are getting brighter and brighter and brighter. You're also getting hotter and hotter and hotter, to the point where you actually have almost purple-colored stars, violet-colored stars. They're very, very hot, very, very bright. We talked about Spica. Spica is one of these brighter blue stars. And then we got this weird patch of stars over here. There's what's called the horizontal branch that goes this way. And then you have two regions. One is called the giants, one is called the supergiants. What do we notice? Well, they're very, very bright. Their luminosity is up here. But they're also really cold. And that's really odd. They're not normal stars. They are no longer on the main sequence. They are no longer fusing hydrogen into helium. They are stars that are transitioning. Just like when you retire from your job, if you're ever lucky enough to have enough money saved up to retire from your job, you go through a transition phase and you start living differently. Well, stars do the same thing. They grow older, they start fusing different elements, and they start trying to keep equilibrium in their core, to keep fusing energy, fusing elements together to create energy. Hydrogen into helium, helium into carbon and oxygen and lithium. And then you try to keep fusing into neon, and then eventually, when you look at the periodic table, you get to iron. Or iron if you're from the Pittsburgh region, however you want to pronounce it. Once you get past iron, as you fuse the elements together, you actually have to put more energy in than you get back. When you fuse hydrogen into helium, you put two hydrogens together, they fuse together and become helium, and a lot of energy gets released. That energy forces other hydrogens to bounce into other hydrogens, and that forces a chain reaction. When you get to iron, if you want to keep fusing, you can, but you have to put more energy in than you get back. So it's still a chain reaction, but it starts killing the star. These stars are stars nearing the end of their lifetime. They puff up and become what are called giants, or in this case a supergiant, a star that is incredibly huge. Let's go back and use our software. Let's use Sandbox Universe to show you the differences in stars. We talked about, these fixed stars and how they are always in these constellation shapes. Let's actually talk about stars themselves. Okay? Let's talk about stars by adding in the sun. Let's start with a simple one. Let's start with the sun. There it is. We've seen this before in our other simulation, but there's the sun. Now, let's compare it to some of the other stars that we talked about during our show, and some stars that we haven't talked about. If you're a Star Trek nerd like myself, you remember the Battle of Wolf 359. The Borg, Captain Picard, all those bad things, right? Wolf 359 is a red dwarf star. This is a red dwarf star. Look at the sun compared to this star. What do you notice? Which one's brighter? Which one is bigger? And after learning about the HR diagram and how we put them all together, which one is hotter? Just by looking at these stars. You know the answers to them, and if you don't, it's okay. The red star is colder. This particular red star, Wolf 359, is smaller than the sun. What other stars did we talk about? Well, we talked about Sirius, didn't we? Seriously, it's really bright at night, and intrinsically, Sirius is very bright indeed. Look at the brightness difference between this little red star, this yellow star, and then this blue star. This is Sirius, which again, you can see tonight. If you go outside and look up, just past Orion to the east of Orion, I should say, you'll notice it's still not all that much bigger than the sun, though, is it? Intrinsically, stars have brightnesses. When you look at the nighttime sky, some stars look brighter than others, and that's because either they're really, really physically big, or they're really, really close by. Think about it. If I put a nightlight on in a room, you might not say it's all that bright, but if I shove the nightlight right in front of your face, one, that's rude. Two, if it's in front of you really, really close, it's going to look really, really bright. See how bright this star looks right now? We're really close to it. But in reality, as we zoom away, you see it's not very bright at all. That is the difference between apparent brightness and actual brightness or luminosity. What other stars can we actually put into this simulation? Well, let's talk about other stars. Let's talk about Rigel. Now, Rigel is Orion's knee star. Remember that? Oh god, I screwed this up. All right, you didn't see that? I just totally screwed it up. I did something dumb. I put it in. So this is the problem, is that Rigel's what's called a blue giant star. Let's look at this again. Hold on, we can do this. I swear, I'm a professional. I swear. There's that blue star, or that's that star. Let's see, we had Sirius. Okay, see, we're all back to normal. You didn't see nothing. We just turned the clock back. We're good. We saved, auto-saved, and reloaded. Wink, wink, nudge, nudge. It's like every video game, right? The boss music started and I panicked. Here we are, looking at these 3 stars. Let's look at Rigel, shall we? You'll notice I'm backing up to bring in Rigel. Rigel is the knee of Orion. Sirius is brighter in our sky, but look at how big physically Rigel is compared to Sirius. This is Sirius right here. That's Rigel to the right. That is a blue giant star. It's very hot, very, very bright. It's not even the biggest one. Remember we talked about Betelgeuse or Betelgeuse, whatever you want to call it, the armpit of Orion? There it is. Where's the sun in all of this? Let's get rid of Rigel real fast. There's our sun. This little yellow dot right there, that's the sun. Wolf 359. There's Sirius. Look at how big Betelgeuse is as a red supergiant. Antares is also a supergiant star. Put it there. Look at how big these things are. This may not make any sense to you. How can a star go from something like this to something like that? Well, it depends on what the star was at the beginning. Some stars are sun-sized or smaller. If they're small, they will become red giants, but they just won't be all that big. If they are super massive stars, if they are huge stars, they will eventually become these supergiant stars. They will just puff up and become huge. How huge are they? Let's look at our simulation real fast. Remember our solar system simulation? This is what we used earlier. Let's imagine if we get rid of the sun and put a different star here, shall we? Let's put Betelgeuse instead of the sun. That star takes up all the space from the sun out almost to that's the orbit of Jupiter right here, this ring around it. Every planet of our solar system on the inner solar system, so Mercury, Venus, Earth, Mars, all the asteroids are currently inside of the actual size of this star. This is what happens when a star grows old. It will puff up and eventually it will die. Now, when stars do approach the end of their lifetime, they do turn into these red giant stars. They get bigger, they consume their solar systems. They can die quietly, or they can die violently. If they die violently, they will explode, and I'll show you an example of that here in a second. If they die quietly, you get something like this. Let's get a picture up here on Still Store. Okay, this is not Mystery Science Theater. I don't have Still Store. But what I can show you is this. Let's get to the proper screen. Boom. There we go. A star like our sun, when it dies, it will puff up, become a red giant star, and then kind of let the outer layers go. And you get something like this, what's called the Ring Nebula. This is a planetary nebula. There's different elements, so hydrogen's going to be the red, and helium, and got nitrogen and oxygen, some of the other stuff. You'll notice there's actually dust particles. Those may have been parts of the solid core being blown out, or maybe there were planets that were involved, which are now dead. RIP planets. F in chat for the planets. Left over is the white hot core, like a hot ember after you barbecue something. That is a white dwarf. The flip side. When you get one of these stars that becomes a massive supergiant star, when you get something, come on, nope, that's the wrong program, go back. You can get what's called a supernova explosion. And when that happens, come on, Fine. When you get a supernova, you get something like this. Kaboom! And you get this violent explosion. And all of this material, again, all that fractally shape going on. All the fractals, and you get what's called a supernova remnant. Looks something like this. They're very, very violent. And they cause interesting things to happen. This is all superheated and super magnetized. You can get what's called a neutron star, which is the core collapsing on itself. All the electrons get stuck with the protons, so they neutralize them. They become neutrons. You get the core of the star. It's about the size of the Earth at this point. So it's super compact, made of neutrons. It's spinning really, really, really fast. That's what we call a neutron star. It's not really a star, but there you go. If that collapses further, that's when you get what are called black holes. And of course, black holes can be small, or they can be massive. So massive that they can be even in the middle of the galaxy. And that's actually the next topic of our discussion here. The galaxy has been in the background of everything we've seen today. It's been in the planetarium, it's been in this simulation, and we just haven't talked about it. What is a galaxy? What is our galaxy? What does it look like? Well, this is what we assume our Milky Way looks like, because we can't get out far enough to see it this way. We see other galaxies in this shape, what's called a spiral galaxy. We've seen them. We've actually looked at them already in our program. But this is what we think our Milky Way looks like. There's variations on this. Some of them have a bar down the middle of them, what's called a barred spiral. At night, this is not what we see. We are in the Milky Way in one of these spiral arms, so from our point of view, the Milky Way looks like this. Something along these lines. With that, I want you to think about it. If you're an artist or a writer, use that as a writing prompt. What if you lived around a star? Let's say you live on a planet, or maybe you live on a moon around a big giant planet that has rings, and it happens to be around a star that at night when you look up, you see something like this in your sky. You don't know about the Earth, so to speak. You're an alien person. What stories could you come up with to make that happen? What songs could you write? What painting could you paint? Astronomy is a really interesting thing. It opens your mind, and it makes you think about various cultures, and it makes you think about various possibilities. Our star, the sun, is not even visible at this scale. We're just one random star kind of out here in one of these arms. Millions and millions of stars. Some of them have companions, so maybe there's 2 or 3 stars orbiting around each other. Some of those may have planets around them. Even if you take the lowest end, what if there's only 100 million stars here? What if each one had 1 planet? How many planets are there? 100 million stars, 100 million planets. But then you have situations like our sun having 8 planets, right? I know some people still say 9. Pluto was demoted. I'm not going to fight over that. We still call it a planet here in New Mexico because Clyde Tombaugh, the person that discovered Pluto, he was from Las Cruces, New Mexico State University, down south. So 9, okay, 8. Let's just call it 8. Let's say there's 100 million stars in this galaxy, and there's 8 planets around each of them. How many planets are there? Okay, now what if each of them had at least 1 satellite or a moon around them? You see how the numbers get huge really, really fast? Are we alone is the huge question. I'm not sure how to answer that. I never know. It makes for fun thought, though. Will we ever get to the day where we're, it's like Star Trek and we travel around the stars, interacting with other cultures? Maybe. Are they going to be violent towards us? Maybe. You never know. But this is our Milky Way. Our Milky Way is not alone. Our Milky Way has some star clusters going in and out of it in this vertical fashion. Those are where the globular clusters are. Remember we talked about open star clusters? Open star clusters exist out along the edges of the galaxy. Those little bright blue stars, that's why you see the blue tinge along the edges. In fact, if this were more accurate, you would see a lot of reddish colored stars around the edges. In fact, let's see, I think we had one of those the other day, didn't we? In our astronomy picture of the day. Let's go back a little bit. Yeah, let's look at Messier 106 real fast. Yeah, perfect. I know this goes back a few days and we talked about this the other day, but this is really pertinent to what we're talking about now. This is not the Milky Way, this is a different galaxy, but it's the same structure. Spiraling arms around the edges, the brighter blue stars around the edges, but you see all the little red splotches? Those are areas where stars are being born. Remember we talked about the Orion Nebula. That is an area of star-forming region, and we'll look at Orion once again here in just a little bit. These are areas where stars are being born, these bright red clouds. And again, you see the orangey red-colored stars more towards the middle, towards the heart of the galaxy. In the heart of most spiral galaxies, you have at least one, if not more, supermassive black hole. So it's a black hole. It's an area where not even light can escape it, but everything is orbiting around it. Did that not show up on the screen? Did you guys not actually see what I was talking about? This picture? I hope it showed up. I wasn't paying attention for a second. The star-forming regions, again, around the edges, the bright red splotches you see all along the edges. It's not in the simulation, but it is in reality how this works. Bluer, younger stars on the edges, redder, older stars more towards the middle. Globular clusters traveling through the plane of the galaxy in a vertical fashion, so going this way, through the galaxy. Now, this is, again, an example of what our galaxy, the Milky Way, looks like. But it's not the only thing in this part of space. Our Milky Way is part of what's called the local group of galaxies. So if you've ever seen the show Power of 10, that's kind of what we're doing in a long-form way. I want you to think about your home address. You have your home, your building, your street address, the street, the county, the city, the state, all that kind of stuff, right? Not necessarily in that order. Your zip code, your prefecture, whatever it is, wherever you happen to live. Ultimately, that all ends with the planet Earth, if you're talking about a street address on the planet Earth. But if you start getting out here, we start talking about planet number 3 of 8 in the solar system. The Sol system in the Milky Way, which is this galaxy here. But there's something much bigger called the local group of galaxies. You no longer see stars here. You see galaxies in the distance, and you see galaxies in front of you. There are different sized galaxies, or different shapes. Some of them are spiral, some of them are elliptical. What are called irregular galaxies, which are like the Large and Small Magellanic Cloud. They're just kind of chunks of galaxies that got ripped off of either the Milky Way or some smaller galaxy that was nearby that got cannibalized. There's the Small Magellanic Cloud. Where's the Large Magellanic Cloud? There it is. Remember, we're in 3D space, so I have to kind of like adjust where we are. You see these if you're in the southern hemisphere. You can see them in the sky. They hang literally below the Milky Way. So when you're talking about above and below, not necessarily top and bottom, because in 3D space, you can orient yourself however you want. But from our point of view, if we consider the northern hemisphere to be top and the southern hemisphere to be bottom, you see all the stuff down here below the Earth, below the equator, below the Milky Way. This is our Milky Way. It is not even the biggest of the galaxies in this group. The biggest of those galaxies is that one right up there. This is the Andromeda Galaxy. The distance from our galaxy, the Milky Way, and Andromeda up here is 2.25 million light years, the speed of light for 2.25 million years to get there. And we just did it in seconds. We're flying around like gods. This is the Milky Way's nearest companion galaxy, spiral galaxy, large spiral galaxy. Now here's the thing. In space, no one can hear you scream. Also, no one can hear you scream, hey, hit the brakes. Because there's no way to scream in space. There's no sound traveling through space like that because there's no air. This distance is being closed between the Andromeda Galaxy and the Milky Way. The gravity, the intrinsic gravity. So you and I, we have gravity. If you're more massive, you have more gravity. I'm kind of a big tubby guy, so I have a lot of gravity. My wife, she's small, she's petite. She doesn't have as much gravity as me. If we were out in the middle of nowhere, she would eventually be attracted to me. Yeah, because I am a bigger dude. I have more mass. Well, in this case, the Andromeda Galaxy is more massive than the Milky Way. And so this distance between these two galaxies being pulled together. And also, this is not even the only galaxy cluster out there. This is, again, the local group of galaxies. There's a larger cluster called the Virgo cluster. There's an even larger cluster called the Virgo supercluster. And that's just one section of the entire known universe. All those dots in the background, those aren't stars. Those are galaxies. Collections of millions of stars, billions of planets. Huge distances away as my phone becomes a squid. If you're not a gamer, you have no idea what I just said. In a few million years, the submissive bottom here, this is the Milky Way, and the dominant top, that is the Andromeda Galaxy, they are going to meet each other. They are going to merge. They are going to have a gravitational dance. This is the hypothetical end of our Milky Way and the hypothetical end of the Andromeda Galaxy, a galactic collision. Now, physically, are stars going to be hitting each other? Probably not. There's a lot of space between the stars. But galaxies do this often. You see galaxies either near miss each other, they kind of fly past each other and their gravity pulls chunks off of them, kind of like the Large and Small Magellanic Clouds. Or they can fully merge like this and create what's called a ring galaxy in some cases, or just an irregular galaxy overall. Ring galaxies are just spirals with the middle part just completely punched out. Looks kind of weird. The supermassive black holes, as you can see, the particles are slowing down the graphics here, but they are in here, bouncing around, kind of trying to find equilibrium, floating around in space. This is the end of the Milky Way, this is the end of the Andromeda Galaxy, but they've formed something new! Order from chaos. Where's the sun in all of this? Well, maybe it got thrown out here. Maybe we're no longer part of the galaxy at all. Or maybe we're still kind of floating around. You know, will our planet Earth still be here? I don't know. That's why I kind of look forward to the day where we can travel the stars, because I'd like to get out of here and go and explore, see what's out there. Andromeda, it's not really visible from the sky right now, in the nighttime sky right now. It is, but it's really low to the horizon, so I'm not really going to talk about too much. There are various galaxies you can see at night right now. Let's go back to Stellarium. There we are again. If you are new to the channel, please like and subscribe. We're on Facebook and Twitch and on YouTube all at the same time. We're literally live streaming to all three. Let's rotate around. Remember we talked about the Big Dipper and the Ursa Major constellation, in which it is part of, earlier. Well, there's actually a galaxy that looks a lot like the Milky Way, just off the tail. I want to be accurate. I don't want to start clicking around. There we go. I'm cheating. You can see kind of where the tail is right here. Find that last star of the tail, and it's just above it to the right. This is what is called the Whirlpool Galaxy, the Whirlpool Galaxy M51, Messier's 51st object in his catalog. It is a spiral galaxy. Now, you did just look at stuff in 3D. I want you to understand this spiral galaxy is closer to us than the galaxy in the background. And so literally, oh goodness, let's go to this. This will be better. Imagine between you and your TV screen or your computer screen or your phone, whatever you're watching us on, imagine between you and that, you have put a spiral galaxy, and then just behind that is another spiral galaxy. I'm sorry, a elliptical galaxy, so it looks like a football. That is not the right one. Why can't you just give me the one I want to see? I want to show them the thing. There it is. This is what it looks like through the Hubble. Much easier and much more clarity. So what we have here, this spiral arm right here is literally being pulled behind it. There is a concept we didn't really talk about, but there is a thing called redshift and blue shift. It's Doppler shifting. You hear it every day. If you hear a siren go by, what do you hear? Gets louder, 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 then quieter, 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 quieter. When it's coming towards you, it's getting louder. When it's going away from you, it's getting quieter. You're compressing the frequency, and then you're stretching it out. With astronomy, you have blue lights, you get blue shift. If it's coming towards you, things turn more blue. If you're going away, things turn more red. If you were to actually measure these things, all of these stars would be blue shifted. They're kind of coming more towards us. These would be more red shifted because they're going away from us. They're actually being pulled by this elliptical galaxy behind the spiral. Really, really cool. And that's just the way it is. There's galaxies that start cannibalizing other galaxies. There's stars that are gigantic. Stars that are all over the place from our point of view. But all the stars you see at night are part of our galaxy, the Milky Way, which, again, looks like that little streak in the sky that you can see when you get away from the city lights. If you live in a city, as you saw from the three-dimensional version earlier, you see lots of city lights and you don't see them very well. We didn't really do that in the planetarium here, but we can show you what that looks like. There we go. Let's change the light pollution factor. Or it can crash. We killed it. Doo-doo-doo-doo-doo-doo-doo. Stellarium has crashed. Wonderful. Let's try that again. Open source software. Sometimes there's bugs in it. I'm sorry. It's not my fault. Let's try it again. Can we get Stellarium back up? Is that a thing? Can we not get Stellarium back up? Okay, Stellarium's dead. It's just gone. There we go. Okay, we're back. Oh, goodness. I don't even know what we were doing in Stellarium anymore. What was I trying to do? Chat, help me. I'm lost. Ah, yes, we're doing we were doing light pollution. That's what we were doing. Thank you. Someone's paying attention. Someone remembered. This is a light polluted city, so New York, Los Angeles, Tokyo. Pick a big, large metro area. This is about what you're going to see. A couple of bright stars. So there's the winter triangle. Very, very obvious. Planet Mars. Not really much else. This right here is a marker that's in the planetarium for a meteor shower. But just ignore that. Get rid of that. There we go. So this is what people are used to. But our ancestors, they had a much more interesting sky. And so they came up with stories. They talked of deities, they talked of great kings and creatures. That's why I love doing this, because we can spend all day talking about stars, we can talk about stories, we can talk about individual planets, and that's why I'm trying to make all these pre-recorded videos. I have one on telescopes already up. The Astronomy 101, I recut it again because I'm a picky person. That'll be up soon. And we'll just be doing Astronomy 101. So if you've never taken astronomy, if you've never done an Astronomy 101 course like in a college level, stick around, follow the channel. And you will slowly, as we get it up, we'll slowly go through Astronomy 101. We'll cover some science, we'll cover some actual math to kind of help you out. But we're going to give you a good basic education in astronomy because so many people don't understand it. That's why I harped and spent so much time on the moon phases earlier in the show. That's why I always talk about the moon phases, why I always talk about the sun. So many people don't understand these things. That's why I'm here. That's why I teach. through this channel. Why sit in a classroom and teach one small group when I can teach on the internet and make it available to everybody? As long as you have an internet connection. I think that sounds like a much cooler way to do things. It's a more interactive way, because chat, you've been talking to me on various sections here, so I appreciate that. Again, we are on YouTube, Facebook, and Twitch all at the same time. We do have a Twitter account as well as a Instagram. I don't think anything gets posted to the Instagram account just yet. Twitter account just kind of retweets a link to our Twitch page, so that's always cool. If you don't follow them yet, please do. There are links to them on our Facebook page. There's links to them on our Twitter page. If you're trying to find it, that's kind of dumb. My apologies. There's links to them on our YouTube page. There's also links on our Twitch page. So feel free to find whichever one you'd like and use it. We do this every Monday and Wednesday and Friday. And of course, we do special events whenever something cool happens. So on Wednesday, when the helicopter goes up, if that's later in the evening, we're going to be live twice on Wednesday for that event. So please stay tuned for that. Please follow the channels. Thank you so much for joining us. We've just done 2 hours of astronomy. We could probably go on more, but I know some people have things to do with their lives, and yeah, people have come and gone, dropped in, said hello. It is appreciated. Stay hydrated. If you haven't done so, please make sure to drink some water. Again, if you're in the Northern Hemisphere, spring and summer are coming, so please stay hydrated. Drink some water, drink your tea, eat your snack that you brought with you to our show here. We do appreciate you showing up. Have yourselves a wonderful afternoon, evening, morning, whatever the time is, wherever you happen to be. We do appreciate your watching us, because you have so many options during the day, and yet you chose to hang out with us. Have yourselves a wonderful afternoon. Please stay safe. We'll see you on Wednesday.